All right, welcome back, everybody. So, we are now rounding the corner. We are almost done with everything we need to talk about before we dive into chaos theory. Before we do so, there's one last bit that I wanted to say regarding bifurcations and what a general theory might look like. And this is the idea behind the center manifold theory, uh, where we are able to study, this is what we're studying in center manifold theory. We are trying to find a way to express the Hartman-Grobman theorem for non-hyperbolic fixed points. So remember, Hartman-Grobman is a way for us to describe the local dynamics near a fixed point, a hyperbolic fixed point. Remember, hyperbolic just means that the real part of all eigenvalues, lambda, are non-zero at and that would be 4 df evaluated at x star, right? We just want to make sure that these guys have a definitive stability, right? There, it can be a saddle, it can be stable, it can be unstable. It just can't be that in between case where it can't decide which one it wants to be. So in a neighborhood of a hyperbolic fixed point, the system, the nonlinear system x dot equals f of x, and this is taken on an arbitrary phase space, is smoothly conjugate to its linearization, right? So quite literally, these two systems have the same dynamics in a neighborhood of the fixed point. This is exactly what we were doing in chapter 6, in saying that we are going to linearize about a fixed point and then study that system instead of the original nonlinear version, because this guy is much simpler to study, and we can go ahead and string a whole bunch of those linear systems together in a global picture much more simply than we can the total nonlinear piece or the total nonlinear system. And this is the essence of the Hartman-Grobman theorem. Our goal is to do the same thing, come up with some version of Hartman-Grobman for the non-hyperbolic fixed points. Okay, so it just means for non-hyperbolicity, we need to have some eigenvalue whose real part is 0, right? Not that all of them are, just need one bad apple to ruin the whole bunch. Okay, so this is the part that we're always a little bit hesitant to go through as instructors, is because there's so much technicality in order to just set up the problem. So I have confidence in you, my students, to be able to parse through these definitions very slowly and very with purpose, right? With a goal in mind. You're not just reading it like a novel. You are trying to understand the definition rather than just copy it down in a notebook. So let's talk about the terminology that we need in order to discuss this idea. So our definition is as follows. We are going to construct a whole bunch of subspaces in our manifold. We are going to talk about invariant manifolds for both the original nonlinear system and for the linearized system. And we are going to need to separate out the different kinds of spaces based on the real parts of the eigenvalues that we find at that fixed point. So we are going to say that this n-dimensional system, so there's a total of n different eigenvalues, including multiplicity, that we're going to have to determine here. Okay, so these guys are allowed to repeat. So the eigenvalues are going to be sigma 1 through sigma n plus, and that'll be all of the stable, right, all the stable pieces. So the real part is going to be negative for all of these sigma i's. So sigma standing for S for stable. So upsilon will be for the unstable portions, right? These are going to be upsilon 1 through upsilon sub n minus 1. And the real parts of these eigenvalues will be positive. And finally, we're going to have that middle case. We're going to have traditional lambdas, because I don't think there's a soft C in Greek. So, I mean, there's like, I could do like a TS, but that's not the same. But the point is that there is there are going to be lambda 1 through lambda n sub 0 eigenvalues whose real parts are exactly 0. And if I'm including multiplicity here, the sums of these guys, sums of all these different, all the different numbers of stable, unstable, and non-hyperbolic pieces have to sum up to the dimension of the original system. So that's the stipulation on these n's. So we're going to denote by E super S, E super U, and E super C. Right, I'll almost never say super, so don't worry about it. We're going to let these guys denote the generalized eigenspaces of the Jacobian matrix at this fixed point x star, associated with the stable, unstable, and C is going to stand for center eigenspace. Okay, so these are essentially just the eigenspaces associated with x star divided into the three different cases for stability. Okay, so that's what the E's stand for, eigenspace. Okay, I'll scroll this a little bit. We're going to extend this now. That's what happened in the linearization. Now we have to go back to the original nonlinear system. So denote by phi of tx0 denote that to be the solution of x dot equals f of x with the initial conditions starting at x0, right, for some small neighborhood of x star, right? So we're just saying that this is going to be the solution of the system with this particular initial condition. And with that terminology, losing my words here. With that denotation, right, that symbol for what the solution looks like, we're going to define WS loc, right, that's how you would read that, WS loc, is going to be the collection of all initial conditions such that the solution of the system starting at x0 tends to x star, not x0, shame on me, tends to x star as t goes to plus infinity. And then you're going to have WU loc, and this is going to be the collection of all initial conditions such that the solution will flow toward x star, not in forward time, but in backwards time. So we've talked about the duality between stable and unstable as being a transformation in time. So stable is, it means asymptotic in forward time. Unstable means asymptotic in backwards time. And these two manifolds are going to be the local stable and unstable manifolds of x star, respectively. Okay, so these are the nonlinear versions. So you think of these E manifolds as being linear, right? They're going to be hyperplanes in general, right? So this n could be an ungodly large number. So these could be very, very large spaces, like high dimensions. But we're accounting for that in the general theory. Now these W's, right, these local stable and unstable manifolds are going to be curved in general. This is why they're manifolds and not just vector spaces. So manifold is just a generalization of Euclidean space. It's something that locally looks like Euclidean space at each point. But I'm getting a little far from the focus here. These are the terms, right? These are the denotations for what we are going to be studying. So in order to complete this definition, you'll notice I didn't have a WC on that list. It's because WC is a little tricky to define. It is possible to define it, but it's more, I think it's more beneficial to us to get an intuitive feel for what it is rather than an analytic definition. So to complete the definition, we employ the following theorem without proof. And oh, it pains me to say without proof. But at the same time, it's kind of a technical argument, and it takes us way too far abroad, right? And if you want a proof, you can look to Carr think that was in the 70s. Carr has a great book on center manifold theory that actually proves this statement. But this theorem statement that I have is comes from Kuznetsov's Bifurcation book, and that is an excellent book. It's pretty dense, but it's very thorough, and it covers a lot of it's these like the bifurcation Bible, so to speak. But anyway, the theorem. This is the center manifold theorem. There is a version of a W manifold, right? There is WC loc at X star, and it's going to be a locally defined smooth n0 dimensional manifold, and it's invariant, which means that if you start on that manifold, you stay on that manifold. You are not allowed to leave it once you're on it. And this is going to be tangent to the center eigenspace at X star, right? So there is an approximate, so EC is a linear approximation to that WC loc at X star, right? So it's the tangent hyperplane. Moreover, there is a neighborhood of this fixed point such that if you start within that neighborhood, or if you are in that neighborhood for all t beyond x0, then the solution is going to tend toward that WC loc for t going to positive infinity. And there is a statement for t going to negative infinity, respectively. So what we are saying is that this manifold is what the solution, what our system wants to contract onto. Things get sucked into or blown away from this manifold. And the manifold WC loc is called the center manifold of X star. Okay, so this guy does exist, and he is locally defined. In fact, there is one manifold that does this. And remark, the theorem is stated for X, or it can be. Oh, I guess I actually fixed that. So originally I had this at face value out of Kuznetsov, and he only did this at X star equals 0. So it's no problem to go ahead and say that this occurs wherever you want to center your manifold, so wherever your fixed point might be. So technically, I wouldn't worry about that statement. If n0 is 0, that means that EC is a zero-dimensional manifold. That means if I go back up here to the original definition, I don't have n0, right? n0 is 0. So I have no eigenvalues with 0 real part. That means that I have a hyperbolic fixed point. So really, this theorem only makes sense to us when we have a non-hyperbolic fixed point. That center manifold will only exist non-trivially at a non-hyperbolic fixed point. And now, technicality aside, why should we care about this? Why did I go through all the trouble of defining this collection of objects? It's because bifurcations occur along center manifolds. Right, and specifically, I have a pair of examples here that'll show you how this might happen. And we did see a version of this back in 8.1 when we're talking about the chemical switch. Right, this is a two-dimensional example of where or how a saddle node bifurcation would occur in a higher dimensional system. And you notice that EC here shows up. Right, this eigenspace shows up when we have our bifurcation point, when we have X star being the non-hyperbolic fixed point in our saddle node bifurcation, right? As we progress along phase portraits, that fixed point doesn't exist until we get past a certain parameter, and that critical parameter produces the saddle node, and that's what this X star is right now. And then once we pass that critical parameter, we have a pair of fixed points, and those fixed points will show up along a slightly perturbed version of this center manifold. But have a look. The blue curves are getting drawn in to WC loc, right? And these red curves are the eigenspaces. These are linearizations of the local stable and center manifolds, which are these curved guys in black. But the point is that notice that our dynamics are completely drawn in along that center manifold. Okay, and that's the whole point here, so we can actually continue this into higher dimensions. We just talked about the Hopf bifurcation. Hopf bifurcations can occur in any dimension, but they always get drawn down to a two-dimensional manifold, right? The center manifold here is two-dimensional. Right? It's because that's the dimension that this has to occur in. It's a codimension 1 bifurcation, but it occurs along a two-dimensional manifold. And that's going to be completely determined as the center manifold along at this fixed point. And notice that we still have a stable manifold going vertically there in black, but because we have a surface for this the center manifold at x star, the tangent approximation is going to be planar. All right, so these dimensions have to match up. So if we had a three-dimensional center manifold, then EC would also be a three-dimensional hyperplane approximation of that guy at x star. But the thing in the cloud here is that the dynamics of the bifurcation are drawn in toward or away from the center manifold, right? If it's away from if we have an unstable manifold piece showing up. So the point is that specifically in the case where we don't have any unstable pieces, the dynamics of this system can be reduced to what happens on the center manifold. And that substantially reduces the dimension of the problem in general, right? Could you imagine we have a 50-dimensional system that exhibits a Hopf bifurcation? All of a sudden you go from 50 variables, a 50-dimensional phase space, down to a two-dimensional phase space. And you can study the dynamics on that smaller space and get a really strong intuition for what the system wants to do along that manifold, and it will tell you what's happening in general. Okay, so this is the setting. This is what we're going to try to do, and we'll see more of these three-dimensional problems, three-dimensional systems when we start talking about chaos, especially when we talk about the Lorentz system. But we're going to elaborate on this clouded statement. So suppose, yeah, we're doing this right, yeah. So suppose that the linearization of the Jacobian matrix is broken down into its hyperbolic and non-hyperbolic components. Specifically, we're going to break this down so that B takes care of all the n plus and n minus pieces. So the real part positive and real part negative, or did I have it backwards? Yeah, real part positive and real part negative eigenvalues. And C is going to encapsulate all the real part zero pieces, all real part zero eigenvalues. Okay, so we've separated this into pieces that are going to identify what is part of the center manifold and what is not, or at least what's part of the approximation, the linear approximation to it. All right, then in its generalized eigenvector basis, we can transform, we can change coordinates from x into u and v, and u is going to take in u is going to be all the hyperbolic pieces, and v will be the non-hyperbolic pieces of that linearization. So we're going to kind of zoom in around x star and try our hand at the Hartman-Grobman theorem for a non-hyperbolic fixed point. And we're going to make sure that we have the linear pieces separated out from the quadratic pieces, right? So we're going to make sure BU and CV are linear pieces. So B is just going to be a constant matrix, right? It's going to be this guy upstairs, and C will also be a constant matrix. But G and H are going to be of square order and higher terms, right? These are all the higher order terms associated with the vector field when we change into the eigenvector basis. So specifically, we need to make sure that G and H of x star and the Jacobians of G and H at X star are all 0. So bear in mind, these guys are vectors, these guys are matrices. I'm dropping a lot of the vector notation here because it just gets too cumbersome and it's going to take away from the overall picture if I try to be too specific. Right? So specifically, the Taylor series of G and H have to begin at second order with respect to U and V. Right? That's all this is saying. So as a consequence of the implicit function theorem, right? This is something that I'm not expecting us to all know, right? This is actually something that we may or may not have seen before. But the implicit function theorem is going to allow us to write the center manifold locally as a graph. And we're going to do this where the center variable v is going to be a function of the non-center variable u. Right? So we're going to try to express everything in terms of just in terms of u's here. So u is going to be essentially the only dependent variable, right? The only autonomous variable that we're going to deal with toward studying these center manifolds. So we're going to go ahead and write v equals capital V of u, and we can then change coordinates in order to decouple the v dot equation from the u dot equation. And this is exactly the reduction principle. At the non-hyperbolic fixed point x star, our nonlinear system is locally topologically conjugate. Basically, there's a continuous change of coordinates, a homeomorphism between it and the system. U dot is bu plus g of u, and we replace the v with the graph, capital V of u, and we completely decouple that bottom equation from the top, right? And this is what we're saying. There's actually a pair of, there are two coordinate changes here that make this work. One is to effectively diagonalize the Jacobian matrix, or choose coordinates where this is in Jordan canonical form. And the second one is so that we can take this piece and get rid of the h. Okay, so this is a pair of coordinate transformations. So the composition of the two of them is still going to be a single coordinate change, or change of coordinates. And this is what we're invoking in the reduction principle, is that we can go ahead and say that the dynamics that occur in this system are effectively drawn into the center manifold and can be completely described on that center manifold. So to reiterate, because the hyperbolic pieces of the system converge either in forward or backward time to the center manifold captures all relevant information about the behavior of the system near the hyperbolic fixed point. Okay, and this is the power of that theorem, that we can reduce the dimension of the system down to something that is much, much more easily handled. And this also tells us why we care about codimension 1 and codimension 2 bifurcations. It's because those dimensions are things we can actually visualize. Okay, I'm going to go ahead and kill the video here, because what's coming next, we're going to start talking about how to actually put this into practice. How can we make computational sense of all of this? Is it just a theoretical tool, or can